This is lecture 33 and we were working with these variables in the last class, Z1, Z2 and Z3. And remember that all of them satisfy equations in the form of this. And to remind you what these were, this Z1 was SYF minus YO, and we had a Z2 these are the three things that we had, Z1, Z2, Z3. I hope you by now are familiar with the notations. Rho is of course a density, and this Z can be Z1, Z2, Z3, this Z. And other than that, we have Cp considered to be equal for all species and also constant. And then S is what? What was S?
Consumption rate of oxidation and flow.
Is it the ratio of consumption rate? What was it exactly? Was it in terms of omega dot? Okay, what was like, I think we calculated S somewhere, isn't it? What was that? For methane it was 4. How did we get that? Methane with pure oxygen. So what was the relation that we used to get S? Okay, so this S is WO nu O divided by WF nu F. So this is the molecular weight of oxidizer multiplied by the stoichiometric coefficient of the oxidizer divided by molecular weight of fuel, stoichiometric coefficient of the fuel. So where is the reaction rate coming in? But that's not wrong either, because this is also equal to omega dot O divided by omega dot F, and there was this curly looking capital omega which got cancelled in the process. Okay, and this we got as equal to 4 for a methane oxygen flame. Just one case we did for getting an idea of the numbers. So you can take ethane air, you can take propane oxygen, whatever. In all those cases you can calculate S. So S is this number which goes in here. Then you have Cp, then you have temperature. What was Q? Heat released in the reaction, isn't it? So we had this Q, and that explains all the variables Z1, Z2, Z3. This is the whole thing that we had. Now, what I pointed out last time is that the Z equation doesn't have a source term. So this has only a transient term, and it also has convection term and diffusion term. So Z is just convecting and diffusing, and there is also a transient term. There is no reaction term. And since there is no reaction term, there is no source term, we consider this Z to be a passive scalar, isn't it? So we called it a passive scalar last time. Passive or conserved scalar, so it changes from one place to the other. This is from one xi coordinate to another xi coordinate because of convection and diffusion. All right, and I think towards the end of the last class we also wrote a small z, correct? Yeah, so there was a small z. Let's try to see what this was. I think we did this in a hurry probably. So there is a small z. So I am striking the middle of this z, striking the midsection of this z to remind you that this is a smaller one. Those other ones were the capital Z's. So this small z is Zj O we had this yesterday in the last class. We had this in the last class. So this is for j equal to 1, 2, 3 because we have z1, z2, z3. And what this ensures is that this is equal to 1 in the fuel stream and this is equal to 0 in the oxidizer stream, correct? Just look at this expression, that will tell you that this is correct. 1 in the fuel stream, 0 in the oxidizer stream, and that is true for all the 3 small z's. Now we have 3 small z's, isn't it? Depending on what j you choose, if you choose j equal to 1, that is if you choose to use capital Z1 here, then you will get a small z1. If you use a capital Z2, you will get a small z2. If you use a capital Z3, you will get a small z3. So there are 3 small z's, and all of them will be equal to 1 in the fuel stream and 0 in the oxidizer stream. Now, what equation do these small z's satisfy? The small z's will also satisfy an equation like this. So how do I get this? Because the small z is some combination, some linear combination with the help of the capital Z, and we know the equation that capital Z satisfies. We wrote that few minutes back. Capital Z satisfies this equation in the box, which is actually the same equation that small z satisfies. So small z is also obviously a passive scalar. But there are 3 small z's, so we can write expressions for these small z's. So let's take one of them. Let's say this is a small z1. So this will be based on this capital Z1, and capital Z1 was SYF minus YO, correct? It had SYF minus YO. Now, this is now Z1 minus Z1O divided by Z1 in the fuel minus Z1 in the oxidizer. Where does this come from? This is the definition of small z.
This will be small z1.
This is actually small z1. So this is small z1. Okay. So let's try writing this out. So this is SYF minus YO minus, what's this? S times 0, because this refers to the oxidizer stream. So in the oxidizer stream there is no fuel, so that YF equal to 0 there. S into 0 minus this is so this is the baseline value of YO in the oxidizer stream. And this is again S YF 0 minus 0. So we are looking at this. we are looking at this. This is basically what Z is, Z1 is, and then we are evaluating that in the fuel stream, because this says fuel stream, this one says fuel stream. Okay. So, this is 0 here, because the fuel mass fraction, sorry, the oxidizer mass fraction in the fuel stream is 0, that is why this is 0. And this we have already written, these two are the same thing. So, we get this, which tells you that this is so that is Z1. So, we can similarly do Z2 and Z3. Now, Z2, what was Z2? Z2 was in terms of temperature, isn't it? What was that? Cpt by Q plus YF. So, we can use an expression like this for Z2, just change 1 with 2. Instead of 1 you put 2, and after doing that you will be able to get a small Z2, correct, same procedure to get a small Z2. So, the small Z2 is going to be something like this. You can work out the details yourself, I will directly write what I got after following this same procedure. So, that is small Z2. This is our Z1 and this is our Z2. Okay. So, we can do the same thing for Z3, and for small Z3 we will get so, we have Z1, Z2, Z3 now. Z1 and Z2 were on the previous page, and we have Z3 here, but all of them are governed by the same equation, isn't it? Denominator will be Tf naught, that is correct. So, this is Tf naught. Right. So, in any case, I am asking you to, encouraging you to work these expressions out yourself. I have done that myself and just directly writing the final expression. If I make a mistake, then you should not be just blindly following that. So, please derive it yourself. So, we have got Z1, Z2, Z3. Now, what does Z satisfy? Going back to this, it actually satisfies this equation, a convection diffusion equation, which does not have a source term. So, this is a nice equation, nice thing to deal with, and the small z's are actually calculated in such a way that they always have this property. So, 1 in the fuel stream and 0 in the oxidizer stream, all of them, because that is how the small z's are calculated. So, all the small z's satisfy, they follow, they are governed by this equation, and they also have identical boundary condition. So, what can we say then? If they follow the same governing equation, if they have the same boundary conditions, then they are all the same. Their solutions will all equal, right. So, we can say that Z1 equal to Z2 equal to Z3, and we can call that actually a small z. And just putting all of these together, we have a small z now, which is equal to Z1. Z1 is this, which is equal to Z2. That is also equal to yeah. So, these three are all equal because of the reason which I just now told you. They are governed by the same differential equation and they have the same boundary conditions. All right. So, based on all this, we can actually also write another expression for small z. This is small z, but we can bring in an equivalence ratio phi, which is s time y f naught by y o naught. So, how do we do this? This z is 1 over phi plus 1 okay. So, is this possible? Please have a look at this and then let us see whether this makes sense or not. Phi is an equivalence ratio. So, that equivalence ratio is this one. This we already have, this we already know. So, from this do we get this? Should be possible. Okay, that is just a little manipulation, that is all. You have to divide maybe somewhere by y o naught to, for example, here if you divide by y o naught, you play some tricks and ultimately bring it to this one. Okay, so, this is in terms of this the same z in terms of equivalence ratio. So, this is sometimes convenient. So, that is why we have got this. So, this is valid and this is also valid. Now, just let us try to again remind ourselves as to why are we doing all this. So, we are doing all this because we are trying to use some tools for diffusion planes. Okay. And I told you that we have to be a little patient, and then first we develop this passive scalars and then go to mixture fraction, and the mixture fraction is going to be useful to us in some way. Okay. Right now we still do not see how mixture fraction will be useful to us. Right now we do not know that. So, what do we know so far? We know that mixture fraction will be easier to solve for. Can we say that? What do we mean by solving for mixture fraction? So, we are trying to solve a diffusion frame problem. So, what do we want actually? We want to get temperature, we want to get the various mass fractions in terms of what?
Position and time.
Yeah, position and time. So, in terms of, let us say, a spatial vector, or maybe I should write xi, because this is what we have been writing, xi. So, if you have a flame, right. So, some place here, some place here, some place there, some place here, some place here, wherever you go, its position can be characterized by these three coordinates x1, x2, x3, okay, in a generalized sense, or it can be r, phi, z. Okay. So, three coordinates, and maybe if the problem is time dependent, then also on time. So, this is what we are trying to get. Similarly, for temperature, we want to get the species mass fractions and temperature. Again, why are we trying to do this? Because that is an interesting thing to do about diffusion flames. And if you get all these profiles, if you see how temperature varies, how species mass fractions vary, then you will be able to say something about the shape of the flame and the height of the flame. And we said that this is important. It is important to know the shape of the flame. And once you get the temperature profile, you can say that you will get the highest temperature maybe around here, or whatever the solution gives you. And you will be able to say that since the flame is here, inside there will not be much oxidizer, outside there will not be much fuel. So, you will be able to define everything. So, that is our purpose. So, what have we done so far, and how does that help us to meet that kind of purpose? We are still quite some distance away from achieving our objective. We are nowhere near getting this. Species mass fractions as a function of xi and t, and temperature as a function of xi and t. We are still nowhere near that, but we have done something else which we hope will be of some use sometime later. That is, we have got something called mixture fraction. Okay. And this mixture fraction, what I am saying is that mixture fraction will be easier to solve for. Solve for means we can get mixture fraction as a function of position and time. By solving for, that is what I mean. Okay. So, that means you have this flame, so this x1, x2, x3 and time. At one place to the other, how does mixture fraction vary? If you are interested in that question, suppose you are interested in that question, then you will try to set up an equation for mixture fraction and then solve it. Okay. Just as if you are interested in temperature, you will try to set up this differential equation for temperature, set up boundary conditions, and then try to solve for temperature at various points, so that you can get temperature as a function of xi and t. You may like to do that, you will definitely like to do that for temperature, you will definitely like to do that for various species mass fractions. So, what I am saying is, if you are interested in mixture fraction and you want to get mixture fraction at various xi and time, you will need an equation for that mixture fraction and boundary conditions. Do we have those? Based on what we have done so far, do we have an equation for mixture fraction? Do we have boundary conditions for mixture fraction? Did we see the mixture fraction equation some time back?
Is that
Conservation equation is the mixture fraction equation, correct? So, we have seen this. We have seen the mixture fraction equation, we also have the boundary conditions. Okay.
It is Z is it includes both YF and Y naught. Separately, how can you find?
Okay, so that's the next question. I mean, how do we? His question is, okay, let's say we can solve for Z, which is mixture fraction. From that, how do we get the species mass fractions, Y fuel and Y oxidizer? Okay, so that's a later question. Fine, that is the ultimate objective. So, I am glad that he asked this question because he is actually thinking about our final objective, and I think he is also hinting that reaching that final objective will possibly be through getting Z. So, first we get Z, and from Z somehow we get the fuel and oxidizer mass fractions. So, he is absolutely right. Now, we will come to that second part, that once we get Z, how do we get YF and Y oxidizer? We will come to that second part little later. But we will do the easier thing first. We are looking at now this mixture fraction equation, this is the conservation equation for mixture fraction, and we also have boundary conditions for the mixture fraction. Okay. So, we can solve this and get Z at various xi and t, correct? But remember the question that I asked, I said that mixture fraction will be, actually not a question, I made a statement, I said that mixture fraction will be easier to solve for, and I am asking you whether you think that is correct or not. Is the mixture fraction equation easier than? Easier is relative, right? Easier than what? Yeah, or maybe individual species mass fractions. Those equations, if you look at those equations, are those equations more difficult? They have source terms. Whereas the mixture fraction equation is a convection diffusion kind of equation. It does not have a source term. So, that is easier to solve. So, source term brings in considerable problems because of the non-linearity is associated with the chemical kinetics term. So, we are not using that. So, if you do not have that, we do not have a source term, we are not using a source term in the mixture fraction equation, then the mixture fraction equation will be easier to solve. Okay, so that is why mixture fraction is a good tool, that it is easier to solve a mixture fraction equation than individual species mass fraction equations or the equation that we have for enthalpy, that is for temperature. So, this will be easier, that is why we developed all this. But it still does not answer the question that was asked a few minutes back as to how do we get the individual mass fractions, temperature, etc. from the mixture fraction. So, that will still take quite a bit of time. But before we proceed further, let's check something. Yeah, let's look at this one and see whether we agree with this. It's just a verification of what we already know. This is a table which I made. Now, it lists these passive scalars. So, we have now this capital Z1, capital Z2. This is actually also a capital Z. This is also a capital Z. By mistake, I crossed it here. This is also capital Z. So, this is Z3. Right. So, I have written these three things. You have to tell me whether these things are okay or not. These are okay? You can write down later, but first tell me whether these are okay. This is correct? In the fuel stream, it should be S times YF naught, because in the fuel stream it is YF naught, and YO is 0 in the fuel stream. So, this will happen, Z1, capital Z1. And let us randomly choose another one. Let us choose Z3 in the oxidizer stream. What is Z3? Z3 is S CPT divided by Q plus YO. Now, what is that in the oxidizer stream? It should be S Cp TO naught, because TO naught is the temperature in the oxidizer stream. Okay. So, the oxidizer stream temperature is TO naught. Then YO becomes YO naught in the oxidizer stream, right. So, you can check this out, this should be all right.
What about Z2 in the oxidizer stream?
Z2 in the oxidizer stream will not have YF, because YF is 0. So, that becomes 0, and okay, there should not be a minus sign. No, there should not be a minus sign. I don't know how that came here. Yeah, there's no minus sign. I think I got influenced by this minus sign. This minus sign is of course correct, right? This minus sign is correct. So, I ended up making this minus also. All right. So, this we know, and I want you to tell me, based on what we know about Z1, Z2, Z3, let us try to complete this table. It's a very simple one actually. So, the variables are here. Let us talk about first this fuel mass fraction. The fuel mass fraction, what is the value of the fuel mass fraction in the fuel stream? We are calling it YF0 actually, isn't it? And value in the oxidizer stream? So, this is no, in the oxidizer stream it is actually 0. And what about the oxidizer mass fraction in the fuel stream? 0. And oxidizer mass fraction in the oxidizer stream? YO0. Okay. What about temperature in the two streams? TF naught, TO naught, TFO naught, TF naught here and TO naught here. What about mixture fraction in the fuel stream and mixture fraction in the oxidizer stream? So, I told you about mixture fractions. So, what are the values of mixture fraction in the various stream? Okay. So, mixture fraction is 1 in the fuel stream and 0 in the oxidizer stream. Is this correct? How do I get this? Is this okay? We are calling it this small z. Is small z equal to 1 in the fuel stream? How do we get that?
Definition
Hmm.
Z, capital Z.
Hmm.
If we put
No.
ZF, then it becomes 1. Or the definition from mixture mass fraction.
No, why capital Z? We are working with small z now, right?
Small z equals to the definition Z minus Z O by ZF minus.
Okay. Small z. So, this is Z1 minus Z1, Z1O. This is Z1F minus Z1O. Okay. So, in the fuel stream it will become equal to 1. Okay. Yeah, so we have done this some time back, just repeating it. And in the oxidizer stream, this Z1 will become Z1O, so it will become 0, so Z will become equal to 0, right. So, this is kind of a revision of what we were doing. Now, So, we understand that we can get a small z, okay, as a function of x I and t, because we have the conservation equation for this and we have the boundary conditions. We understand the boundary conditions, we checked the boundary conditions ourselves in the last two tables, fine. Now, the next part will be that if we have got this, how do you get y k's and temperature from z? So, that can be an important question. So, to do that, we will take a case where the chemistry is infinitely fast, okay, irreversible infinitely fast chemistry. So, this is the question, and the assumption we are making actually, but this will be an easy thing to do, is that we will assume irreversible infinitely fast chemistry, irreversible infinitely fast chemistry. So, what do these words mean? Irreversible means that fuel reacts with oxidizer to give you products and the products do not dissociate back and give you fuel and oxidizer, right. So, it is all irreversible. And infinitely fast chemistry, did we discuss infinitely fast chemistry few lectures back? Yeah, to some extent we did. In fact, I do not know whether I have the slides now. I had shown you some plots, correct? Yeah, I think I have these. Yeah, I will show you something like this, isn't it? So, infinitely fast chemistry means the reaction is very fast in a very thin zone, infinitely fast in an infinitesimally thin zone. So, that is what was happening. We saw that fuel diffuses towards the flame from the fuel stream, okay, and the oxidizer diffuses from outside the flame, from the ambient oxidizer field. So, that diffuses and it comes towards the flame, they meet at the flame. So, they mix at the flame and they burn as soon as they mix, okay, and that is possible if it is an infinitely fast chemistry. So, they are coming and meeting and immediately burning. There is no chance of leakage. We also spoke about leakage some time back. We said that if the flame here, think about this flame here, if this was somewhat weaker, then some oxidizer will seep into the fuel side and some fuel will seep out towards the oxidizer side. We discussed all that, isn't it? So, that is infinitely fast chemistry when you get a very, very thin flame. And the main significance of this is that you have a sharply defined, a clearly defined flame, and inside the flame there is no oxidizer and outside the flame there is no fuel, all right. So, this much we remember from a previous discussion. Now, we are going back to some kind of a assumption similar to this. So, we are assuming infinitely fast chemistry, infinitely fast irreversible chemistry. So, if you have a situation like this, the flame structure that we get, it is actually known as a Burke-Schumann structure. So, this was given by two people, Burke and Schumann, and this was in the 1920s probably, do not remember very well, but long time back. This was one of the early solutions of combustion. Okay, there were no real computers to speak of those days. So, this was all analytical work. So, they developed this theory based on all this infinitely fast chemistry, and lot of later developments in diffusion flame theory is based on what Burke and Schumann had done. So, this is a Burke-Schumann structure. We refer to this Burke-Schumann structure as the one for infinitely fast irreversible chemistry. Okay, so in that case, let us see what happens on the fuel side. It is easy. We can say what is YO on the fuel side. What is that? 0, 0 everywhere, because this is your flame, this is the fuel side, this is the oxidizer side. As soon as you are within the flame, there is no oxidizer. So, oxidizer is 0. Okay. It would not have been so easy if the chemistry was finite, isn't it? So, this is YO. Now, can we get an expression for YF in terms of Z, in terms of mixture fraction, which relates to your question? Can we get YF as a function of Z, which is mixture fraction? Can we do that? Let us try. We have an expression for Z. So, that Z is 1 over 5 plus 1 this is the expression for Z1, where I have actually just brought in phi, the equivalence ratio. Okay, this is Z1, this is not complicated, fine. So, can we use this expression to get Y fuel as a function of Z on the fuel side? That is the question. Easy? Very easy. So, if you do that, then it will be like this. It is YF like this. Just a little bit of work. Again, it will be your job to reach here from here. And we write this as so we have a ZST, which is a stoichiometric Z. The ZST is the stoichiometric value of Z. So, this is nice. If you look at this, this is nice. This is what we have been talking about, that if we can Z as a if we can get Z by solving the mixture fraction equation, if we can do that, then maybe we can use that Z value to get YF. So, we are going back to YF, it is possible from Z. From Z we can go back to YF. So, we get YF as a now, since we know Z as a function of x, assuming that we have solved for Z, if we have solved for Z, then we have got Z as a function of xi and t, right. So, once we have got that, put that Z here, then you will be able to get YF at various places. So, you will be able to get YF at various places on the fuel side. This is valid only for the fuel side. You do not need YF as a function of Z, etc., YF as a function of xi outside the flame, right, because there is no fuel outside the flame. Under this assumption, under the assumption that we are making of irreversible infinitely fast chemistry. Okay. So, this will give you this. Now, the next question is, what is ZST? ZST is the stoichiometric value of Z. So, I can ask you to suggest what you think is the stoichiometric value of ZST. Z is, of course, from last page, from last page. So, what is the stoichiometric value? Stoichiometric value will be phi equal to 1. So, stoichiometric value will be actually ZST will correspond to flame, and at the flame we say that YF is equal to YO is equal to 1. Okay. So, we are not saying anything about phi as such. Phi is, what was phi? S times YF naught by YO naught. So, there is some phi with which we are doing this problem, but we are defining Z stoichiometric corresponding to the flame. Okay, we are not saying phi equal to 1. Right? We will have to come back to that later. And why is not phi equal to 1? If you want to ask that question, we will have to come back to that later. But right now, what I am saying is, at the Z stoichiometric will correspond to the flame. Why did I write 1 here? I do not know. This is 0. Okay. At the flame, YF and Y oxidizer will be 0. Why? Same story as before. What we had done last time, not last time, few classes back. YF is 0, YO is 0 at the flame. Remember, this is on this plane. Okay. So, if both are 0, then Z stoichiometric will correspond to that. So, Z stoichiometric will be how much? 1 by 5 plus 1. Because this is 0, this is 0. So, 1 over 5 plus 1. So, what we can actually do, and we may not do it today, but we can calculate for various kinds of fuel oxidizer combinations. We can actually calculate what is Z stoichiometric, because see, you know how to calculate S. For example, we were doing this methane oxygen case where S turned out to be 4, right. So, we can calculate phi, we know S, we can set YF naught, we can set YO naught, we can get a value of phi. Once we get a value of phi, we can get a value of Z stoichiometric also. So, Z stoichiometric is something which is useful because we are writing YF in terms of Z stoichiometric. Okay. So, inside the flame we have YF as a function of Z. So, let us appreciate the fact that this is actually important, because again summarizing, what did I say? I said that it is easier to solve for mixture fraction. Solving means you can get mixture fraction at various spatial points. Okay. So, you can get mixture fraction as a function of xi. So, you got mixture fraction. Once you get mixture fraction, within the flame you can get fuel mass fraction using this simple relation. So, the difficulty is only in solving the mixture fraction equation, because that is the differential equation. It is a convection diffusion equation. So, that is more difficult, but once you have solved that, it is actually easy to get fuel mass fractions. But we have to remember that this is subject to the assumption of irreversible infinitely fast chemistry. Okay. We have to remember that, and the solution that you see on this slide is actually valid only within the flame zone, only inside the flame zone, that is on the fuel side. So, this is YF as a function of Z, and we can actually also get on the oxidizer side. We can do a similar exercise on the oxidizer side. On the oxidizer side, we can easily write YF equal to 0, correct? On the oxidizer side, YF is 0, and we can get YO, and I will leave that to you. So, YO is YO naught 1 minus Z divided by Z stoichiometric. What else do we want? Now we have fuel and oxidizer both inside the flame, outside the flame. So what else do we want? We also want temperature. And how do you get temperature? Again, similar sort of exercise, but we'll have to bring in not small z1, something else, isn't it? Because small z1 is what we used to get the mass fractions, but small z1 doesn't have temperature explicitly. So we'll have to use something else. So maybe we can use something like this one for temperature. We can use something, we can use this, and then use various conditions on the fuel side and the oxidizer side, and then also use Z stoichiometric as 1 over 5 plus 1 to finally obtain expressions for temperature on the fuel side and temperature also on the oxidizer side. Okay. Now we are running out of time, so I'll just, as I told you that you have to use this, you have to use this expression and apply various conditions like no oxidizer on the fuel side, no fuel on the oxidizer side. You can bring in all these and also use Z stoichiometric as 1 over 5 plus 1. Then you will get expressions for temperature. So on the fuel side, so this I am doing in a hurry, but you can cross check this and let me know if there is any problem. This is on the fuel side. So that's on the oxidizer side. In the interest of time, I am stopping here, but I am asking you to verify. It's not difficult, as you saw for the fuel mass fraction and the oxidizer mass fraction. It's actually not difficult. So you have to do the same thing. It's just a little longer for temperature. Okay, so again, this is a nice thing because this gives you temperature as a function of z, and hopefully you have already obtained z as a function of xi. So you have got all solution. Okay, so what have we not done? We have not explicitly solved for z. I just told you it's possible, isn't it? But this, at least by the end of this class, now we understand the overall framework. We have this mixture fraction, solve for mixture fraction. Once you get mixture fraction, if you are also in a position to assume irreversible infinitely fast chemistry, then on the fuel side as well on the oxidizer side, you can separately get fuel mass fraction, oxidizer mass fraction, and you can also get temperature. Okay. But we don't stop here. In the next class, we'll have to see more details of this and hopefully look at what kind of maximum temperatures we get in diffusion flame and some other associated issues. So we'll stop here. Thank you.